Alright guys, a little quick tutorial for you. We're working in section 3.7 today. 3.7 is all about related rates. We've got a lot of examples by now. If you want to see lots of examples, check out a previous video I made for you. The lecture video, the lecture series has 2 hours worth of examples of stuff just like this. So this is just a quick question, number 11 in 3.7. The setup is this. We have a square baseball diamond, okay, home plate, home plate, first base, second base, third base. The sides here are 90 feet each. We have a runner, excuse me, we have a runner over here between second base and third base, running toward third base at a rate of 23 feet per second. And the question is, at what rate is this distance S, the distance between the player and home plate, at what rate is that changing? So clearly, as the runner runs from second base to third base, we can depict a right triangle here, and the distance S is the hypotenuse of that right triangle, and that hypotenuse is shrinking as the runner gets closer and closer to third base. So as with a lot of these related rates problems, the Pythagorean theorem pops up. Again, we have a right triangle, and we are trying to figure out how fast S, the hypotenuse here, is changing. So let's write the Pythagorean theorem just with the current variables. Okay? Remember, the idea here is to relate the variables that we're working with. We want to relate S and X. And typically, whenever you have a right triangle, but you're not dealing with angles, typically you're going to use Pythagorean theorem. Okay, that's usually a pretty safe bet. So let's see here. We could say what using the Pythagorean theorem? We could say that x squared plus 90 squared equals S squared. Okay? That relates X and S. Now, if we take the derivative with respect to t, what do we get? Well, we get 2x, but we just took the derivative
of an x term with respect to t, so we have to multiply by,
excuse me,
dx dt.
Now, if I take the derivative of 90 squared, I get 0. With respect to t, with respect to x, with respect to any variable, the derivative of a constant is always 0, so that goes away. And then we have the derivative of s squared gives us 2s, but we're taking it with respect to t, so we have to multiply by ds dt. Now notice here, we have a 2 on both sides of the equation, so we can reduce this equation slightly. We could just say that this is equal to x dx dt s ds dt. Okay? Now what information do we know? Once we take our derivative of our related rates equation, we need to figure out what are we given and is that sufficient to solve? Okay, it says player is 22 feet from third base. That's x. So 22 equals x. So we can rewrite this equation just substituting in the knowns, and we could say that 22 is equal to x. Now, do we know dx dt? Let's see here. Player is 22 feet from third base, running at 23 feet per second. So what does that tell us? The player is 22 feet away, running at 23 feet per second toward third base. What does that tell us about the change in x? Is x, this distance right here, is that getting bigger? Or is that getting smaller? Or is it staying the same, nothing changing? Well, I think if the runner is going 23 feet per second towards third base, we can see that x is shrinking at a rate of 23 feet per second. So dx dt is 23. That's kind of the tricky thing, is that these related rates scenarios aren't going to tell you dx dt equals this, ds dt equals that, solve for dy dt, or whatever. You have to translate, and when we see running at 23 feet per second, that's telling us that something's changing at 23 feet per second. What is changing? Well, look at our diagram, that's x is changing. So dx dt is 23, so make that substitution equals s, oh, sorry. Do we know what s is? Currently, no. We've used up all the information we've been given, at least the initial information. 22 feet from third base, actually we haven't used that yet. Oh, yeah, sorry, yeah we have, x, 22. 23 feet per second. Now, s and ds dt are left over. Which one am I solving for? Well, I want to figure out how fast is this distance s changing. So that's what I'm solving for. So I don't want to find anything to substitute for that, but I do need to figure out what s is. And what usually happens in these Pythagorean type situations is that I need to consider this specific situation. 22 feet from third base. Consider that specific right triangle, and I think if we consider that specific right triangle, when the player's 22 feet from third base, we know that this side is 90, we'll then be able to figure out what s is in that particular situation. So let's see, just over here real fast. We want to consider this equation where x, well, this side is 90, where x is 22, and s is unknown. So clearly the Pythagorean theorem tells us that 90 squared plus 22 squared equals s squared. Okay? I have a feeling this is not going to give us a nice answer, but that's alright. 90 squared plus 22 squared, that's 8584. So if I take the square root of 8584, do I get a nice number? No, I don't get a whole number. So I'm just going to leave this as the square root of 8584 equals s. And then I can make that proper substitution over here. I know what s is. It's the square root of 8584 times, then we have what's left over was that ds dt. And now you can see I have an equation with only one unknown. I can easily solve for that one unknown by dividing both sides by that radical. So I can say that 22 times 23, which is 506, divided by the square root of 8584 is equal to ds dt. So that is how fast, that's the exact solution for how fast s is changing. Oh, you know what? I just realized I made a mistake. Just hit me. Going back here, dx dt, I just thought about something. My answer is positive. Okay? My answer is positive, but this distance is decreasing, so it should be negative because s is getting smaller. So where did I go wrong? I went wrong right here. Very easy thing to fix. 23 is negative. X is decreasing, getting smaller, so the rate of change is negative. which means there's a negative sign right there, which means there's a negative sign right there. Okay? Because x is getting smaller and s is getting smaller. So both of those derivatives have to be negative because they're getting smaller. Okay, cool. That was an easy fix. What is this number approximately? Let's see here. Negative 506 divided by the square root of 8584. Approximately, it is, let's see, negative 5.461. So, of course, we typically prefer exact answers, but depending on the context, the directions of a test or homework or quiz question, you may be asked to round. Oh, the last little thing here is I should always specify units. Both of these are in what units? Well, it's a linear distance. We're not talking about area or volume or anything. We're just talking about a linear distance. We're in feet per second. So feet per second. Okay? So again, that's the approximate answer. This is the exact answer. Exact answers are almost always preferable unless, for some reason, directions specify to round to some certain number of decimal places. So cool. Just to recap, player 22 feet from third base, running towards third base. So this distance is initially 22 feet, but it's getting smaller. That made the change in x with respect to t negative 23. We use Pythagorean theorem to relate x and s. We take the derivative of both sides, do a slight bit of reducing, then plug in the information we know. We had to do a little bit of solving over there to find this. Solve for the one thing that's left over, which is exactly what we're looking for. And if we need to round, take care of any rounding at the very end. Don't forget your units, especially on a test. Hope it's been helpful. If you have more questions, just let me know.